So today we are talking about 2.2, linear functions and relations, and we want to be able to identify them and write them in standard form. We're also going to work on finding our x and y intercept. So here's what standard form looks like. It has the x value with the coefficient in front of that, the b value or the y value with the coefficient, and then your constant over on the other side of the equal sign. So the x-intercept is where it crosses the x-axis, and that's also where the y value would be equal to 0. The x-intercept is where the graph crosses the y-axis. Did I say x-intercept? Y-intercept. Crosses the y-axis, and it's where the x value is 0. So first we're going to say whether these are linear or not. So a linear function creates a straight line when it's graphed. So if you look at this, you can also tell just by the information that's given here. So if we look at this, we have an x value that is just to a single power. So this would be a line. This would be a line with a y-intercept of -5 and a slope of 2. So this is linear. And it's in this very familiar format, the y equals mx plus b, that we're going to talk about this chapter as well. If we look at b, b would not be linear because it has this cubed on here, which makes this a cubic function. So I'm going to say not linear because it's a cubic function. Part C, this is also a line with a slope of 7 and a y-intercept of 4. They just have them flipped around here. So this is linear. So we have the line 7x plus 4 there. Example 2 says we have a linear function f of c. So here we're in that function notation. We're naming the function f, and we're using a capital C as our variable. It's equal to 1.8c plus 32. And this can be used to find the number of degrees Fahrenheit, which that's what this whole thing is representing, is degrees Fahrenheit. So that goes with this. It can be used to find the number of degrees Fahrenheit that are equivalent to a given number of degrees Celsius C. So this is saying that this capital C represents degrees Celsius here. So part A, on the Celsius scale, normal body temperature is 37 degrees. What is it in degrees Fahrenheit? So using my little function here, I'm going to take 37, since that's in Celsius, and we're going to substitute that in. So this is saying f of 37, meaning I'm taking my function and I'm substituting in a 37. And then we're going to plug that into our handy dandy calculator. So we have 1.8 times 37 plus 32 is 98.6. Maybe you've heard that value before. That is normal body temperature in Fahrenheit, 98.6 degrees Fahrenheit. Part B says there are 100 degrees Celsius between the freezing and boiling points of water. This is why the metric system makes so much more sense, and Celsius makes more sense than Fahrenheit, because freezing is 0 and boiling is 100. Such nice numbers. Where ours, there's 180 degrees in between those 2 points, and our freezing value is at 32. Which means water boils at 212 degrees. So not as nice a numbers as the Celsius system, but whatever. So we want to know how many Fahrenheit degrees are equal to 1 Celsius degree. So we can actually set up a proportion here. I have 100 degrees Celsius is the difference, and 180 degrees Fahrenheit. So how many Fahrenheit degrees are equal to 1 Celsius degree? So I'm going to put 1 degree Celsius here, and I'm going to put x degrees Fahrenheit here. Now if you remember with proportions, you can use a cross product. So that means I am cross multiplying and solving. So 100 times x is 100x, and 180 times 1 is 180. And then I would divide both sides by 100, and that would give me 1.8. and we are degrees Fahrenheit is what it was asking for. So this means that 1.8 degrees Fahrenheit is equal to 1 degree Celsius there. And last example says we are going to take this y equals 3x minus 9, and we're going to put it in standard form, and then find the x and y intercepts and use them to graph. So if I'm going to put it in standard form, I want the x's and the y's all on one side, and I want the constant term on the other. So, sorry. If I want to get the x's and y's all on the same side, I'm going to move this 3x over to this side. So I'm going to do that by subtracting. So I can't combine those because one's a y and one's an x, so I'm going to just rewrite it like this. So now we have it in standard form. So now I'm going to find my x and y intercepts. So the x-intercept is where y is equal to 0. So using this standard form format, I'm going to plug a 0 in for the y. And I'm going to solve. So 0 minus anything, that 0 doesn't do anything. I would divide both sides by -3, and I would get x equals 3. So my x-intercept is where x is 3 and y is 0. So on my graph over here, that's right here. Now my y-intercept, the y-intercept is where x is equal to 0. So I'm going to take this format again. This is why the standard form is really handy. And I'm going to plug the 0 in for the x this time. So now if I simplify this, anything times 0 cancels out, so this just becomes y equals -9. Which means I go down, this is where x is 0 and y is -9, so that would be right here on my graph. And then I'm going to try to draw a straight line, make it look nice. So there's my line. Now if you think about this from what you remember in the past, you could look at this and say, oh, well, I know that that has a slope of 3 and a y-intercept of 9. And that's the same thing we have here. Here's my y-intercept of 9, and I would have went up 3 over 1, up 3 over 1, up 3 over 1, and I would have got that same exact line. All right, so on this last example, or sorry, these two for you to do, it says find the x and y-intercept of this. It's already in standard form for you, so you just have to do this piece and graph it. So, and then, oh, sorry, it doesn't need you to graph this one, my bad. It wants you to graph here. Graph one that has an x-intercept of -3 and a y-intercept of 5. So you're just using that information to graph on here. All right, and lastly, your joke. Where are fish in orbit? They're in Trouter space. All right, I hope you have a lovely day, and make sure you're kind to someone today.